Okay, so we're going to start our second lecture. In the first class, we talked about units. I talked a little bit about the, let's see. We talked a little bit about the significant figures. So let me start off with a short discussion on significant figures, and then we are going to work on vectors. So the idea again is significant figure makes only sense with respect to some measurement. Okay. Now, for instance, suppose you are measuring a length, and you are using a meter scale which has the smallest unit. The smallest unit is a centimeter. Okay. So what you have, therefore, is suppose you measure something to be, say, 3 meters and 25 centimeters. Okay. If you want to write it in terms of meters, you might say, because 25 centimeters is just 0.25 meters. So you can say that you have a measurement of a length, which is 3.25 centimeters. Okay. So we say that here we have 3 significant figures. Now, mathematically, 3.25 and 3.250 are the same thing, because in fact you can keep on adding any number of zeros after here. Now, do you then increase the significant figures from a 3 that we had here to 4? Okay, and that's not correct, right? Because in physics, 3.250 means something different from 3.25. Now, if you had instead a meter scale that measures the smallest unit is a millimeter, then you could measure up to 1,000th of a meter, right? Because 1 millimeter is 1,000 of a meter. Okay. So then you can make measurements. You could have measurements like 3.251. Okay, which means this is 3 meters, 25 centimeters, and 1 millimeter. Okay, so in that case, it makes sense to have 4 significant figures, because that's what your measuring instrument is measuring, right? So in this case, because your measuring instrument is not precise enough, then you can just end it at 3.25. So 3 significant figures. Here, because your measuring instrument can make more finer measurements, you say you can keep up to 4 significant figures. Okay, so this is how the significant figures are related to how we measure. Now, you could have a measurement like 3 meters, 25 centimeters, and 0 millimeter, and this would look like 3.250. And this means that if you're using 4 significant figures here, that means you're using a measuring instrument which is measuring up to a millimeter, right? But since here the measuring instrument was measuring only up to a centimeter, it doesn't make sense to add more zeros here. Now, there are various rules on, when you work with significant figures, like if you multiply significant figures, how, what are the rules for multiplying significant figures? So, or if you're adding or doing any other operations, and that's something that, you will learn in your lab. But the basic idea is that if you multiply 2 quantities, suppose you have, you're measuring, say an area, and somehow a length and the width. So the length is known, say, up to 3 significant figures, and somehow the width is known up to 4.653. So it's known up to 4 significant figures. Then in the area that you get, L times W, you're going to keep only the number of significant figures for the one which has the lowest number of significant figures, right? So in this case, if you multiply this, you're going to get, so let's see. So you have 3.25 times 4.653. So you get, if you punch it in your calculator, you're going to get 12225, but you're going to keep only up to 3 significant figures. So you're just going to keep up to 15.1, whatever. So this is meters, this is meters, this is meters squared. Okay. So that's pretty much what very briefly what we are going to deal with significant figures. Now, as I said in the in our homework, I'm not going to insist on keeping the right significant figures, but when you are going to do the lab, you have to make sure that when you write your answers, it's written in terms of the appropriate significant figures, and that's something that you're going to do in the lab. Now, if you have any questions about significant figures, you can come and talk to the TA during the tutoring session, or you can talk to me during office hours. Okay. So what I want to do is now start looking at vectors, and this is the main one of the fundamental concepts that we need for this course. So it's a very good, useful to have a very good conceptual idea of what the vectors are. Okay. So we start with, I might not follow exactly the book, order of the book, but let's start with that. So the first thing are scalars and vectors. And the idea is that basically we have quantities in physics which can be just represented by a single number. So example of scalar is it's your mass. So for instance, you might have a mass of 50 kilograms, and that's all that is required to describe the mass. So that's all that is required to specify the mass. Or it can be temperature, right? And the temperature could be, say, 37 degrees Celsius, which is pretty much like the temperature we have now. So again, it's a number. That's all we need to specify. Okay. But many of the quantities that we deal with, and especially in this course, we are going to learn about motion. This course is on mechanics. Mechanics is describing the motion of objects. And we will find that there are certain, and that's what we're going to do in the next chapter. What are the quantities that we require that are needed to specify motion, right? The motion of an object. And some of the things that we already know about are things like displacement, or and we'll kind of define them later more precisely, or velocity, and so on. Okay. Now, and we'll talk about forces. Now, these are objects that are quantities that not only have magnitudes, but it also have directions. So, for instance, if you say that you're moving at 50 miles an hour, in what direction? What you'd also like to know is in what direction you're moving. So, if you're going to the east or west, you can end up in different directions and different positions depending on, the direction you're traveling. So even though you will be traveling at 50 miles, whatever, 50 miles an hour so there is a difference between traveling 50 miles an hour to the east or traveling 50 miles an hour to the west, right? So the direction is important. The same with forces, right? So you can apply a force, and the unit of force we'll find is Newton, but it matters in what direction you're applying. So you can apply a force directly horizontally, you can apply a force at an angle, and or you can apply a force in the vertical direction. So just by specifying, saying that I'm applying a force of 5 newtons doesn't make any sense unless you actually specify the directions. So vectors are quantities that require not only its magnitude, but also direction. So unlike scalars, vectors are quantities that have magnitude and direction. So we have to specify. So what this chapter is about, how do we, so the first order of business is, how do we describe a vector, or how do we specify a vector? So in our description, we should have two information. We should have information about its magnitude, and we should also have information about its direction. Okay, so let's start with the simple geometric description, but later on we are going to deal with more analytic description, because that's what we are going to, it's going to help us in solving, in calculating quantities and solving problems, right? So, but the geometric description is useful to have an idea of the basic concept of description. Okay. And so a geometric description is that if you want to represent, suppose a velocity vector, and we are going to write a vector with an arrow here. So, and sometimes a vector is written with the bold face letter, but we are going to just use the vector here, because that means that it is, unlike a scalar like mass, it also has a direction. So we're going to write the vector here, okay? So suppose we have a vector, a velocity vector, and you're moving at, say, let's say 50 meters per second, and you're going in a certain direction, right? So what we do is we can draw a straight line, okay? So we can draw a straight line, say this is, we can make a unit, or we can make a scale. So we can say, okay, 50 centimeters of length. So we are going to say that 1 centimeter is equivalent to, this sign is equivalent, so this is equivalent to 1 meter per second, okay? So 50, a length of 50 centimeter represents 50 meters per second, okay? So the length of this line gives you the magnitude. So the length of this line gives you the magnitude of the vector. So length is the magnitude of the vector. And the direction is given by the arrow here. So this gives you, this is the direction. So this is a directed line segment. So it's a line with an arrow. The arrow gives you in which direction you're moving, right? So if you're moving in the horizontal direction, so if you have a velocity vector of 50 meters per second, and you're moving along the horizontal direction, then I can just draw a straight line like this. So this is 50 meters per second, and this is the direction. Okay. So this is the geometric description of vectors. Okay. Now, let's see. Now we're going to work with the algebra of vectors. The book starts with vectors in one dimension, but I'm not going to work on that. I'm going to directly go to vectors in two dimensions. Okay, so we'll talk about vectors in general. So how do we work with vectors? And often you have to, so this is called the algebra. Why do you need algebra? So by algebra, we mean that suppose we have a vector A and say a vector B, we will often need to do some operations on it. For instance, we might have to find what is A plus B. So that A plus B is another vector here, okay? Now this might be the case if, for instance, if you have a mass and there are two forces acting on it. So, you might have a force which is acting on this direction, force. So that's one vector, and you might have force acting on this, okay? So now we want to find what's the resultant of these two forces. So we'll have to figure out, so the resultant force is going to be the sum of these two forces. So we'll have to figure out how we are going to add these two vectors, okay? Now, geometrically, so before we kind of do that, let's make some simple rules. The first result is that, so I said that if you have a vector A, we can represent it with a line, okay? And the arrow here gives you the direction of the vector, okay? So the first rule is that you're free. It doesn't matter from where your origin is. You can actually move it. You can move the vector parallel to itself, right? So if I move this vector here, this is also the same vector, okay? So these two vectors are parallel to each other and they are the same, okay? So it doesn't matter from where you decide to start drawing your vector, as long as you move things parallel, and if you draw a vector which is parallel to each other, both of them are the same vectors, okay? So one of the simplest geometric so the law of so let's start with some basic algebra of vectors, okay? So let's start first with addition and subtraction. Okay, well, so suppose we have a vector which is A, and then and you have a vector B, okay? And you want to find what is A plus B. Now we're going to find that we can actually do these vectors in the analytic way, but it'll become easier using the analytic way, okay? And the rule is there are two ways of adding the vectors. One is the triangle law, and we can do A plus B. It doesn't depend, it's the same as B plus A, okay? It doesn't matter whether you're adding A to B and B to A. So the rule is that if you're doing A plus B, then you start with the vector A, and then you move the vector which was here, remember? So this was the vector B. And since I'm allowed to move the vector B parallel to each other, I'm going to take the origin of the vector and put it at the head of vector A. So I'm going to put it here, okay? So this is also the vector B, okay? Now the sum of the vector is given by this. So if I say the vector C equal to A plus B, then this is given by this. So this is the resultant vector, C equal to A plus B. So that's how you would add vector. The other one is called the parallelogram law. And the idea there is that, if you have the vector B and you have the vector A, then you just complete the parallelogram here. So, and the diagonal vector is the vector C. So C equal to A plus B. Also, you note that it doesn't matter whether I'm doing A plus B plus B plus A, because if I were to do B plus A, I would take the B vector here, and the A vector was here. So I'm going to move the A vector to the tip of the B vector. So I'm going to move it here. So this is A vector 2. And then I'm going to just go from, so the rule is that after you have moved the B vector here, you go from the tail of A to the head of B, right? Okay. So I'm going to go from the tail of B to the head of A, which is this. Okay. So this is, as you say, this is the same, C equal to A plus B. Now, you can add more than one vector. So for instance, if I do A vector plus B vector plus C vector, the idea is that, you can add first A plus B, and then you get a vector, and then you can add another vector C. But on the other hand, if I just, suppose I've got a vector A here, I've got a vector B here, and I've got a vector C here, I can do the same rule. So the first thing I'm going to do is I have the vector A, then I'm going to move the vector B here to the head of A. So this is B, okay. Then I'm going to move the C vector to the head of B. The C vector is kind of going this way, okay. So remember, the C vector was here, and the B vector was here, okay. And so then I'm going to join the tail of A. So this was the tail, and I'm going to join it to the head of B. So this is going to be my resultant vector, okay. So this vector is R, is going to be A plus B plus C. And you can keep on doing it in this way. Okay. How do you subtract vectors? So let's go with so suppose you want to do A minus B, and the idea is that it's the same as addition. So what you do A and then plus of minus B, okay. So we have to define what is minus B. So minus B vector is just a vector which has, so if you have a vector B here, the minus B vector has the same magnitude but the opposite direction. So this was the vector B. So, yeah. So if this is the vector B, then minus B is just the vector which has the same magnitude but opposite direction. This is minus B, okay. So minus B has same magnitude but opposite direction. Okay. So now if I want to do A minus B, so as I said, this is going to be A plus of minus B. Okay. So again, suppose I have got an A, and I've got a vector b here. So I'm going to draw the minus b vector, which is here. Okay. Now I'm going to add a to minus b. So which means that, again, I'm going to move the b vector and I'm going to move it to the head of a. So this is minus b vector. And I'm going to join the tail to the head of the minus b vector, which is this vector. Okay. So this vector is the resultant vector equal to a plus of minus b, which is a minus b. Okay, so this is the resultant. Okay. The other thing that we are going to do is multiplication of a vector by a scalar. And we'll do some more multiplications later on, but I'm not going to do it the geometric way. I'm going to do it the analytic way. Okay. So multiplication of a vector by a scalar is basically, if you have a vector like a, and so what is 3a? So 3a is a vector, has the same, the direction as a, but the magnitude is 3 times. So for instance, if I have a vector a, which is here, and suppose I draw it with a length of, say, whatever, 10 centimeters, right? Then the 3a vector will have the same direction, but 1, 2, 3, okay? And so this will be 30 centimeters. This is 3. Okay. So you might get equations like, what is 3a vector plus 2b vector? So first we are going to construct the 3a vector, what's going to construct the 2b vectors, and we are just going to make the vector addition. So this is the geometric, and but more useful and something that we are going to use more frequently is the analytic way of doing the vectors. Okay, and so we are going to go into the analytic form. Okay, so this is section 2.2. It's called the coordinate system. So there are two ways in which we can represent a vector. One is the Cartesian way, and one is the polar way. So let's start with the Cartesian way. So basically what we are going to do is we are going to draw a coordinate system. Okay, and it's your choice to do which coordinate system you choose. Okay, so I'm going to choose this to me by y-axis and this to me by x-axis. Okay, now if I draw a vector, now I can draw a vector here, and my tail is going to start from the origin here. And so in this coordinate system, the x, I can represent this point by the coordinates ax and ay. Okay. So the vector a is going to be, we can write it in terms of its coordinates. So we're going to say ax and ay. So that's how we can represent a vector. So it tells you that I draw a coordinate system, and if I specify a vector by ax and ay, I have to go a distance ax along the x direction and ay along the y direction. So suppose I have a vector which I write as, it may be a velocity vector with, say, 3 meters per second and 1 meter per second. Again, I choose a scale, so I will choose that 1 centimeter equal to say 1 meter per second. Then I can represent it by a coordinate system. So the coordinate of this point, the vector A, is going to be because 1 meter per second is 3 centimeters, so this coordinate is going to be 3, so 3 centimeters and 1 centimeter, which means that I go 3 centimeters along the x-axis, 1 centimeter along the y-axis, and I get my vector. So this is the vector. So this vector represents, which is the same thing as 3 meters per second and 1 meter per second. Okay. So that's the Cartesian. Now, what is the magnitude of the vector? The magnitude of the vector is the length of the vector. And so we're going to write the magnitude. This is how we write the magnitude. So we're going to write the vector, and we're going to put some, it's like the absolute value that we use. And it's given by the right angle or the Pythagoras theorem. We're going to say ax squared, let's say y squared. Okay. So for in the example here, where we had say 3 and 1, the magnitude of the vector is going to be square root of 3 square plus 1 square, which is square root of 9 plus 1, which is square root of 10 meters per second. So let's do the polar version, polar representation. And the polar representation is going to be given by a vector A, which is given by its magnitude and direction. Okay. And the direction is given by theta. And again, this is the very important point. Theta will always be the angle measured from the positive x-axis. So, so suppose I have a vector here. Again, this is my coordinate system. This is my x. So I can draw a length, say 1/5. And I'm not going to put the unit. We can put the unit here. And it's going to be specified by the angle. And the angle, I will start going counterclockwise. So this is going counterclockwise. So I'm going to start here and going this way. Okay, so this is the angle. For instance, this would be say 30 degrees. So the vector A is going to be 5 and 30 degrees. Okay, so it's given by the magnitude here, and it's given by the angle. Okay. Now, of course, from your trig, we can easily work out what the connection between the polar and the angle, polar and the Cartesian representation. So suppose I have a vector A, and this magnitude is A, and this angle is theta. Then I can complete the triangle here. So I know this distance is AX, and this distance is AY. And so what I can do, I know that AX over A, sorry, is cosine of theta. So I get AX equal to the magnitude of A cosine of theta. And then I have got AY over the magnitude of A is sine of theta. So I get AY equal to A sine of theta. Okay. So, you know, we can go from the polar representation to the Cartesian representation. Okay. And also from this, you can also get the angles if you want to do tangent of theta equal to, say, AY over AX. Okay. So that kind of gives you the angle. Okay. So let me do an example. So suppose I have got well, I forgot to bring my notes. Just okay. So let's take some example here of vector, and I had some worked out examples, so we can do it. So suppose, as an example, I have you're given a vector which is suppose you have a vector A which is, say, 5, and again some units. So let's just take meter per second, and the angle is 45 degrees. Okay. Now this is a simple one, so I can do y and x, and then I have the vector which is 5, and the angle is 45 degrees. Okay. So what I have to find is what are the Cartesian, what is A, what is AX and AY. So I can just use AX using this formula. So this is going to be 5 cosine of 45 degrees. So that's going to be 5 meters per second. And cosine of 45 degrees is 1 over square root of 2. AY equal to 5 sine 45. So this is going to be 5 meters per second, 1 over square root of 2. Okay, so that's pretty straightforward. Okay. But now let's do the opposite. So suppose I give you a vector which is say 3, and it's some unit, and 4. Okay, and so you have to find the polar description. Okay. So remember, the polar description involves A, and you have to find the angle theta. Now, from these equations that you have here, we can actually find A and theta, and we already did that. So A is going to be given by square root of AX squared plus AY squared. And then there are 3 ways of finding theta. One, again, from this equation here, you can find that once you have found A, then from this equation, AX over A equal to cosine theta, you can find theta equal to cosine inverse of AX over the magnitude of A. Or you can do AY over A equal to sine theta, and then you want to do theta equal to sine inverse of AY over A. You're going to get the same answer, okay? Or the other way you can do is AY over AX equal to tangent of theta, and so theta is just going to be tan inverse of AY and AX. Now, it's sometimes useful to find out in which quadrant your the theta is, to actually evaluate all three and to see that you get the correct answer. Now, in this case, we have 3 and 4, so we can find their magnitude. So it's just going to be 3 square plus 4 square, which is going to be 9 plus 16 is going to be square root of 25, so which is 5. Okay, and we can use any of this. So we can use tangent of theta equal to ay over ax, so which is 4 over 3. So theta equal to tan inverse 4 over 3. Okay, and I don't have I'll have to find a calculator. You can find that. Okay, so that's your answer. Okay, so we can go. So these are the two ways in which we are going to represent a vector. So either it's in the Cartesian way or the polar way, and we can go from the Cartesian to the polar way. Now let's do the algebra, right? Okay, and it's most useful to work with the Cartesian representation or the Cartesian description of vectors. So first is, if you have a vector A, so let me introduce you to the idea of unit vector. So let's start with this. So A is ax, ay. Okay. So if the negative A vector is just going to be given by negative ax, negative ay. Okay, so that's a negative of a vector. Multiplication with a scalar, if you multiply, say, 3 times a, then again, if a is ax, ay, 3 times a is just going to be 3ax, 3ay. Okay? So multiplication by a scalar. Okay. Okay. How about addition of vectors? So the addition of vectors is very simple. Okay. Vector addition. So suppose you're given a vector which is ax, ay, and you're given a vector b which is bx and by. So what you're going to do is you have say y and x, and suppose you have the vector which is a, which is ax, ay, and you've got a vector b which is bx, by. Okay, and the resultant vector, so let's write the resultant vector is a plus b, and the resultant vector is given by the component rx and ry, and rx is you just add the x component of the two vectors, so it's just going to be ax plus bx, and ry is just going to be ay plus by. Now if you draw this, you can easily see that, so suppose I draw the vector here, b. Okay. So this distance is ax. If I draw this here, this distance is bx. If I draw this here, this distance is ay. And if I draw this here, this distance is by. Okay. So now if I complete this parallelogram here, and this point is the resultant vector. So I draw the resultant vector here, and the resultant vector r is just ax plus bx and ay plus by. Okay. So you can see that the x coordinate of this is just the sum of ax plus bx, and the y coordinate here is sorry, this is by. Okay, because we moved the vector here, so this is the b vector. Okay. So this is the y coordinate of b. This is the x coordinate of. This is the y coordinate of. So this distance is the y coordinate of the vector a. This distance is the y coordinate of the vector b, which is from here. And this distance is the x coordinate of vector a, and this is the x coordinate of vector. So this is the rule, okay? And after you do that, you can find, again, after you find Rx and Ry, you can actually find what is the what is the magnitude and direction of R. So we are always going to use the we're going to use this Cartesian way of adding vectors. And I'm going to do some problems in the class. Let's quickly give you the polar way of adding vectors, though we are not going to use much. So polar way. So in this case, we are going to represent vectors by the angle and direction here. So suppose this is vector A. So this is A and this is angle is theta A. So theta A is the angle which is measured from here, okay? And suppose this is a vector B, which has a magnitude. So this is magnitude of B. So I'm just going to write as B and as theta B. So theta B is the angle which is measured here, okay? And then what is the resultant vector? So the resultant vector is going to be again given by, so let's draw it here again. So we are going to complete the parallelogram here, and this is going to be the resultant vector R. This is going to be A. This is theta A. This is theta B. And the magnitude of the resultant vector is given by the, so the resultant vector is R, and the magnitude is given by R squared equal to A squared plus B squared plus 2AB cosine of theta B minus theta A. Okay. And this is called theta, and theta is the angle between the two vectors. We are mostly going to use the Cartesian way of adding and subtracting vectors, right? So that's the way, that's the thing that we're going to use. As a quick example, what I want to do is I'm going to just give one example and then we're going to stop, and I will record one more short videos on the dot product and cross product, maybe later in the day or maybe tomorrow, and I'm going to maybe post it again, but let's see. Okay, so here is an example. So suppose I have got, let's say I want to do, let's do an example. So suppose I have got a vector which is 3, 1, and I've got a vector which is, say, 2, -5. Find R, which is 2A plus 5B. Okay. So remember, so you have to use all the rules, right? So A equals 3, 1. So 2A is going to be 6 and 2. Oh, sorry, right. And B equals 2 minus 5. So 5B is going to be multiplying by 5. So it's going to be 10 minus 25. Okay. Now, so 2A plus 3B, you're just going to add the X and Y components. So that becomes 6 plus 10, and then becomes 2 minus 25. So that becomes 16 minus 23. So that's the result. And once you have got the AX and AY, you can get the magnitude and you can get the direction, just like we did. Let me introduce, before we stop, very quickly to the idea of unit vectors. So it's I and J vectors. So again, let's look at the Cartesian here. So you have the vector A. Okay. Now, in the Cartesian way, this is the same as doing AX and AY. Okay. Now you can see that we can think of this vector A being made out of two vectors. One is a vector which is going along this direction, okay, and one is a vector which is going along this direction, okay, right. So the vector AX, AY can be written as AX 0. So we're going to call this the vector AX 0, right? And it can be 0 AY, okay? Because if you know the law of addition of vectors, this vector plus this vector gives you this vector. And again, we say that, you know, when we add these two vectors, you add the X component. So AX plus 0 is AX and AY plus 0 is this, right? So this vector can be resolved. So we say this vector is resolved into two directions, 1 and 2. Okay. So this is how it is. But at the same time, we can take the AX out and call this 1, 0. And you can take the AY out and it's called 0. Okay. Now these are vectors which are called unit vectors. So this vector is called, we're going to write it as a unit vector I, and AY is going to be called a unit vector J. Okay. So I hat is a unit vector along x-axis, and J hat is a unit vector along y-axis. Now, what is the meaning of a unit vector? A unit vector has unit magnitude. Which means that I vector, which is 1, 0, if I take the magnitude of I vector, I get square root of 1 plus 0, which is 1. If I take the unit vector j, which is 0, 1, so if I take, it's going to be square root of 0 plus 1, which is 1. Okay. So these are the unit vectors. Okay. Now you can define a unit vector in any direction, right? So suppose you have a vector A. So we can define a unit vector along A, and it is written by A hat. A hat is a unit vector along A. Okay. And A hat is defined to be the vector A divided by the magnitude of A. Okay. So for instance, if I have a vector which is 3, 1, then I know the magnitude of A is going to be 3 square plus 1 square. So that's equal to 9 plus 1, so it's 10. So the unit vector is going to be A, which is 3, 1, divided by square root of 10, which is going to be 3 square root of 10 and 1 square root of 10. Now, if you want to write it in terms of I and j, this can be written as 3 square root of 10 I vector plus 1 square root of 10 j vector. So once you write this vector, the vector addition and everything becomes very simple. So suppose I write a vector as 6i plus 7j, and I write a vector b equals 2i plus 8j. And then if I want to find the resultant vector, which is 3a minus 2b. So I'm just going to do 3, and for a, I'm going to write 6i plus 7j, and I'm going to do minus b equal to 2i plus 8j. Okay. So this becomes 18i plus 21j, and this becomes minus 4i minus 16j. Okay. And so what I'm going to do is now I'm going to combine all the i's and the j's together. So it's going to be 18 minus 4i, and it's going to be 21 minus 16j. So this becomes 14i plus 5j. Okay. So we're going to actually start doing this in terms of I and j. So we're going to always write the vectors in terms of I and j. So instead of trying to maybe do another lecture, let me just finally do one more thing, and that's the multiplication of vectors. So there are two multiplications. One is called the scalar product, and I'm going to do some more examples on that. Scalar product of two vectors. So if I have got two vectors A and B, then the scalar product is written as A dot B, and it's given by the magnitude of A and the magnitude of B and cosine of the angle between them. Okay. So if you have a vector A and you have a vector B, and the angle between them is theta, so theta is the angle between A Now, it doesn't matter whether you take this angle or you take this angle. So, just take the angle between A and B. Now, if you write angle A to be the vector A to be this, and B to be Bx, By, you also get, so this is our final formula, it is also Ax, Bx plus Ay, By, which is the same as A, B, cosine of theta. Okay. So this is very useful to find the angle between A and B. Okay. So as an example, suppose I give you again two vectors. So suppose I do vector say 3, 1, and B equal to 1, 1. Okay. So now if I want to do the so suppose the problem is find the angle between the two vectors. So what I'm going to do is I'm going to do A dot B, which is equal to the magnitude of A, the magnitude of B, and cosine of theta. Now what is A dot B? So I'm going to use the formula. A dot B is AX BX plus AY BY. So this is going to be 3 times 1 plus 1 times 1. So equal to 3 plus 1, which is 4. And so therefore I get 4 equal to magnitude of A, which is 3 squared plus 1 squared, magnitude of B, which is 1 squared plus 1 squared, and then cosine of theta. So 4 equal to square root of 10, square root of 2, cosine of theta. So I get cosine of theta equal to 4 divided by square root of 10, square root of 2. And then I get cosine inverse. So let me stop here. The last product is called the cross product, and we are going to kind of discuss that in class. So that's going to be A cross B, but I'm going to mention that in the next video lecture. But I don't have any problem on the cross product in the homework. I'm going to discuss in class. Okay. Okay, so let's stop the recording.